Hello all, this is Naren from School of Chemical and Biotechnology SASTRA. This video is part of the Fluid Mechanics for Process Engineers course. We are on the learning capsule learn.3 talking about non-Newtonian fluids. The suggested readings are the books by Munson and Fox on the fluid mechanics. Now let's see the mathematical relationships, the expressions that are typically used to describe the non-Newtonian fluids. The one commonly used expression to describe non-Newtonian fluid is what is given here, which is the Ostwald-Dewey equation. Now, just a small note that this is not one person, these are two people. This is a German scientist and this is a British scientist whose work formed the basis of this expression. Now, the expression states that you have a shear stress that is equal to a flow consistency index kappa and into a shear rate raised to the power n. So you can see here this is in contrast to the Newtonian fluid. So because in Newtonian fluid this was used to not be there, so that means the value of n would be 1. And you guessed it right, based on the value of n we can classify the fluids as Newtonian and non-Newtonian. So these are essentially the non-Newtonian fluids. If the value is 1, then the flow behavior index. So if the value of the flow behavior index is 1, then the flow consistency index kappa that we write is the same as the viscosity of the fluid. If the value of n is greater than 1, those fluids are called to be the shear thickening fluids or the dilatant fluids. And if the value of n is less than 1, those are shear thinning or the pseudoplastic fluids. Let's see in this plot how this looks like. So if you have a shear stress versus shear rate and you plot the experimental data and you find out the slope to be constant, right, the slope to be constant value, certainly this n will become 1 and these are the Newtonian fluids. Now see about this fluid which is there in the red color. Suppose if these are the experimental data and if you draw by a smooth curve, this is how the plot looks like. Now if you carefully observe and you connect each of the points, okay, and try to see the slope, and you can see that the slope the slope decreases as you keep on increasing the shear rate or the deformation rate. This means as you keep increasing the applied force, it becomes more and more easier for the fluid to deform, because this slope characterizes the internal friction, or in other words, here the slope characterizes the viscosity in terms of Newtonian fluid. We don't use the word viscosity here. Let me temporarily use the word as apparent viscosity or a pseudo viscosity for a non-Newtonian fluid. So this pseudo viscosity or an apparent viscosity decreases, so that means the flow is getting facilitated. So this is essentially of a shear thinning fluid, or it's a pseudoplastic fluid. So this is a pseudoplastic fluid. See the behavior with respect to the one which is shown in blue. Now you can easily observe that as you apply more shear, the viscosity increases. So that means the fluid resists now the deformation and acts as if it is going to be more tougher for you to deform. This is the characteristics of a dilatant fluid or a shear thickening fluid. So in continuation with our discussion in the learning capsule 11.2, this pseudoplastic is something that we see is of paint, and this dilatant is something that we see in terms of a quicksand or oblak. Sorry, this is not quicksand, is actually a pseudoplastic fluid. So I would oblak. Quicksand, if you actually see, it will be a rigid as long as you don't apply a force, but the moment somebody steps into it, it yields. The person falls into a sand. So this is the case of a pseudoplastic fluid, because normally you would look like as though it is a sand and you will be able to stand on it, but you will know that at the moment you stand on it, the moment you apply a force on it, the moment you walk, it actually cleaves, it actually yields, and we actually fall. So quicksand is a classic, another classic example of a pseudoplastic fluid. Let's go to the next slide and see what is this apparent viscosity that I talked about. Now, if you use this Oswald-Dube model, so you can write the shear stress as kappa times gamma to the power n. So this is the flow consistency index and this is the flow behavior index. Now, if you can make a slight rearrangement and look like as if it is an apparent viscosity times the shear rate, you can understand that the apparent viscosity can be given as a multiple of a flow consistency index kappa times the shear rate power n minus 1. Now this clearly shows that apparent viscosity is a function of flow, unlike in Newtonian system where the viscosity is only a fluid property. Now why we call this as a function of flow? Because you can clearly see that this is a function of gamma dot, the shear rate, and the shear rate, for example, is captured by how the velocity, how the flow is actually happening into the system. So this apparent viscosity is no longer a fluid property, but it is rather a flow property because it depends on the flow system. We also have other models for other kinds of fluid behavior that we saw. Like for example, the Bingham plastic, the model that is being adopted is shown here. Shear stress is equal to tau naught plus mu times gamma dot, and this tau naught is the yield stress or the residual stress. Now you can clearly see from this expression, this is of the form y equal to mx plus c. So you have a definitive intercept. So there is a definite intercept for this kind of fluid. As long as your applied shear stress, suppose let us say that this is a value of 10 pascals. So if your applied shear stress is less than 10 knots, so suppose if your applied shear stress is 8, so that means the point comes here, you can see that, which means the gamma dot is 0, so there is no deformation. So if your applied shear stress is less than the yield stress, you don't see any deformation, you don't see any response. The moment the shear stress is greater than equal to the residual stress or the yield stress, the moment the applied shear stress is greater than the yield stress or the residual stress, it behaves like a Newtonian fluid, and you can see that it will keep on responding to the applied shear. This is a classical behavior that is expected from a Bingham plastic. It's not only we have these two models, we also have a combination of these two models as long it is observed. And one such is a Herschel-Bulkley model. This is this is as old as of about, I think, 1920s. I suppose it is formulated from the experiments, where you can see a combination of an yield stress and also the flow behavior and the consistency index. So taking clue from this, if you draw on a rheogram the shear stress versus the shear rate, now we can expect lots of such behavior. So this is the classical Newtonian, but you have here pseudoplastic, you have here dilatant, this is your Bingham plastic, and this is a combination of Bingham plastic and a pseudoplastic behavior, right? So you can have various combinations of these. That brings to an interesting question, that is it possible to tune the fluid behavior, how the fluid responds to an applied shear? What causes the fluid to have a different behavior like this? This is all the subject matter of rheology, As part of this fluid mechanics course, we are not going to go in detail, but I would appreciate that you go back and look into the reasons, the microscopic reasons, and how the fluid system as a whole can be modulated, right? Can be orchestrated. We can to behave for a given application, and certainly these have interesting application. The one very commonly celebrated application is of an armor for a defense system. We want armor to be very lightweight, but the moment the bullet strikes, we want the bullet to be captured in the armor and it should not affect the person, right? So this is possible by tuning the fluids, and this rheology study of fluids has a very good overlap also with how the colloidal system behaves. With this, I come to the end of this capsule. Thanks for watching the video.